I'm Drew Perry, and along with Michael Krapes and Tanzan Mustafa, we have our presentation on polypropylene machine learning, creating essentially a soft sensor. So the introduction and background, this is dealing with plastic production, specifically polypropylene as mentioned in the title. It's created in slurry reactors where different monomers are introduced to a catalyst where the chains grow and hydrogen introduced to stop those polymer chain growth. It's important that these polypropylene chains are the correct length so that they can be used in the application that's desired. And this can be determined to an appropriate degree by using the melt flow rate, or MFR as we will be referring to it. And so we did this using machine learning in Python with some various Python packages, including pandas, numpy, seaborn, matplotlib, and sklearn. The goals of this are to essentially determine from readily available variables, such as the propylene feed rate, hydrogen propylene ratio, reactor pressure, etc., and be able to determine from these an approximate MFR to decrease the frequency of manual samples taken. This is also known as a soft sensor. Now, as a group, we individually came up with a couple different methodologies. So we'll be going over 3 different methodologies and their independent results before comparing them together and analyzing the differences, the benefits and detriments of each, and then concluding. So this first methodology is relatively straightforward and similar to what we've done in class. Of course, first we have to observe and clean the data using methods such as head, describe, skew, and the correlation methods, where we see the correlation heat map up in the top right, along with scatter plot matrices and box and whisker plots to check for outliers. We also looked for correlation between the variables and removed any missing data. So in the bottom right, we can see 2 scatter plot matrices because for some of the variables were found to be quite skewed, with a skew value from that dot skew method of plus or minus 0.75 is about where the line was drawn. If they were right skewed, which 4 of them were, then the natural log of that variable was taken to improve the skewness, and it did produce better results. So on the left scatter plot matrix, we see the results before this natural log was applied, and on the right, we see the results after the natural log was applied. And you can see there are some slight differences in how specifically those 4 variables are distributed. The only outliers we removed, though, in this methodology were any where that hydrogen ratio, H2R is the variable name that we're using, where that was 0, because when taking the natural log, of course, we cannot take the natural log of 0. This only removed approximately 15 entries, so it wasn't significant in reducing the total data. And so you can see the MFR box and whisker plot, and you can see that there do exist some outliers that were left in for this methodology. So continuing on, linear models were used with the sklearn linear model Python module. And so 4 different models were made with the initial X values, the initial Y values, that pair, the initial X values, and the log of the Y values, the log of the X values and the initial Y values, and the log of those X values and the log of the Y values. So those 4 pairings. And first were used with the entire data set to get an idea of the performance. Following that, we used the train test split from sklearn with a 20% test and used the same random state to check for any sort of overfitting, and followed up by doing the same but dropping 1 X variable each time just to get a comparison and make sure any highly correlated variables were addressed. And then finally, we used train test split again, but with more than 1 random state, actually states 0 through 10,000, tracking the best and the average MSE and R squared values. However, we don't really end up using MSE later on in this methodology, as taking the log of the MFR, that Y variable, means comparing models across the ones with the log and without the log of MFR isn't really possible. We could compare the two with the log of MFR and the two with the initial values, but the same results were reflected in the R squared, and so for ease, it was left out. And so the results, so first, those linear models with the entire data set, we can see that R squared varied, but generally improved slightly by taking the log of MFR, that Y variable, and improved more significantly taking the log of the X variables. And of course, doing those together produced the best results. Then the comparison for overfitting, we can see the various R squared values for the train and test data sets. And we see approximately the same sort of distribution that we might expect given the performance of the entire data set. And then following through with dropping each variable, each of these performed generally significantly worse, though dropping level or the temperature variables produced relatively close results. Just with this brief look into possible overfitting, it doesn't seem like our model is overfit with these two simple tests. So then finally, using that train test split with a bunch of different random states and tracking the best and average, we can see that it's largely reflecting the results of the full data set. And these are the values of the test data set. And on average, again, the log of both sets of variables, both the X set and the Y set, performed the best on average, though we do see that the log of X with just the initial Y variables, the initial MFR, did perform better maximally, but we are largely concerned with the performance on average. And now I will be passing it off to Michael to address his methodology and results.
Thank you, Drew. For our second methodology, we took a different stance for analysis. We went ahead and used a dataset profiler tool, which is essentially a collection of all the pandas methods for investigating a dataset put into a single tool that can make it very simple to investigate a dataset. Next, we visualize the dataset and looks through any obvious to see relationships to a scatter plot matrix. This would allow us to at least see if there is a relationship between variables and if we can use that to train our model or if there's any obvious outliers, along with the box and whisker plots, and took care of them through there. Next, we prepared the data set by removing potential outliers, and then we removed bias by using a standard scalar. We didn't need to use a robust scalar since we've already taken care of outliers. And then finally, we train and test the model by choosing a model and visualizing the effectiveness of the model compared to other models to see how it was. We did our analysis with Y data profiling to analyze the data set. Through our analysis, we were able to find that the data set had the following characteristics: 2,564 rows in the initial data set and 2,484 rows after removing 80 rows with missing values. Now, since it's only 80 rows, we still have a good number of rows to train and test the data set on. If it were more than 80, we likely would have had to interpolate values. All columns contain real value numbers except for the date and time, and MFR has the highest correlation with H2R and pressure, which can be seen on the matrix on the right. That's significant because that will have a great impact on how we train and visualize our models. The scatter plot matrix has no obvious relationships or patterns as can be seen on the right. Additionally, we added the natural log of MFR to fix the skewness and see if there's any other relationships with that particular modification. except there is two groups that seem to appear when it comes to MFR. We see two essentially hills from the histogram, and splitting the MFR into two groups and graphing them together can provide further ideas into how these two groups are affected by the variables, which could help with future training and ideas. Here we have the MFR split into two groups. The one contains the first hill and the second one contains the second hill. And on the right, we have the scatter plot matrix of both groups. And what's interesting about this is there isn't an obvious pattern to it, but it begs the question on why there's two. And perhaps a full explanation would require a professional in the field of this sort of production. And then we prepared the data set by training and testing it. First, we removed the 80 rows with missing values. And again, we still have a good number of rows, so we didn't have to interpolate. And then we added the natural log of MFR column and removed the initial MFR column. This was to reduce the skewness and improve the overall performance of the model. And then we removed the date and time, since that doesn't really have an impact on the results of our model. And then we removed potential outliers as seen through the box and whisker plots. And we used the sklearn standard scaler to remove potential bias from large differences in ranges between data sets. And again, we didn't use a robust scaler since we're already going ahead and removing the outliers as seen through box and whisker plots. On the left is box and whisker plots before outliers were removed. And on the right is after they were removed. I see this still leaves us with 2,464 rows after removing the outliers. So as you can see, we removed H2R has a value near 1, so we removed that. And C2 had a value above 100,000, so we went ahead and removed that. And temperature had values above 85. And the thing is with those is that could be an implication of many sorts of things. And without having a professional who knows the production of these materials, going above 85 can mean either there was an incorrect reading or perhaps there was a malfunction in the system and it produced a bad batch. And as you've seen with the MFR, there were some values that were above 30, very few values, so we went ahead and removed those. And then we did training and testing of the data set. The data set was split into two sets where 80% was used for training and 20% was used for testing. This seemed to work well, so this is what we did. Initial training and testing was based on the variables that have the greatest impact on MFR, and of course the natural log of MFR. And we produced numerical and visual results based on these variables and MFR. And the final results are based on all the variables and MFR. Using sklearn and select k-best, we discovered which variables had the greatest impact on MFR. The two variables that had the greatest impact were H2R and pressure, as could be seen on the graph on the right. Initial training, testing, and visualizing are based on these variables to gain a great understanding of the final model. Here we can see we have some linear model regression models along with their R2 scores. We can see we have the testing set R2 scores and the training set R2 scores. Most of the models are rather similar, with Lasso having the lowest scores. And these are the average scores. So these have been tested through multiple iterations. And as can be seen, all the training scores are above the testing scores. This hints that there might be slight overfitting. However, the difference is only very slight, so it isn't too overly fit. We went ahead and tested some nonlinear regression models and scored their R2 scores. And we have the testing and training set scores. And as can be seen, these scored significantly higher than the linear regression models. And what's interesting about these is they have the same pattern where the training sets often score higher than the testing sets. And for a third methodology, we have Tanzim introducing for us an additional methods and procedures.
Thank you. My name is Tanzim Mustafa, and I'll continue this presentation by explaining the third methodology, experimented with the polymer reactor dataset. So for this methodology, first of all, we remove the time feature as it does not have much significance with the melt flow rate or MFR. Then we add the natural log of MFR as another feature, as this is a better way to express the data when using linear regression methods as it linearizes the feature. Using the describe method of pandas, we analyze the features of the dataset, and then we find the null values in the dataset and drop them. We end up removing 80 rows, and the new length of the dataset is 2484. After that, we use some data visualization techniques to further perform analysis of the data, as can be seen in the two figures. So the figure on the left displays a pair plot of all the features where the diagonal shows the distribution of the values for each feature using histograms. The off diagonals shows scatter plots of each pair of features against each other. This figure basically helps us visualize the relationships or any correlations present between the pairs of features. The figure on the right shows the correlation heat map between all the features, which gives a quantitative number between -1 and 1, as well as a color shade from dark blue to dark red, corresponding to how correlated each feature is. We can observe, for example, that pressure and H2R show the most positive correlation with the natural log of MFR. On the other hand, the C3 and the catalyst shows the most negative correlation. So moving on to the next slide. This slide shows the utilization of a histogram to visualize the distribution of MFR and the natural log of MFR. So we can see, for example, on the left figure, that the count for each bin of MFR, and the figure on the right shows the count for the natural log of MFR. This slide shows some more data visualization techniques, this time using a join plot to display the relationship between two variables. So a join plot combines several types of plots into one and tries to show the distribution as well as their joint distribution. In this case, we use a regression line to show their joint distribution. And the figures, we show the joint plot of the two most positively correlated features with the natural log of MFR, which are H2R and pressure, as well as the plots for two most negatively correlated features with the natural log of MFR, which are C3 and the catalyst. So moving on to the next slide. In this slide, it shows how we used a box plot from the matplotlib library to help us detect any outliers present in the dataset. So in the figures, we observe how the box plot clearly displays the median, quartiles, and any potential outliers that are present in the dataset. The individual points that fall outside of the whiskers of each plot can be considered to be outliers, and we basically process the dataset to remove these points. So in this slide, the specific ranges for each of the features are given that have been used to remove the outliers. So for example, for MFR, we remove any outliers, or we remove the ranges that exceeds the value of 30. And basically, before removing the outliers, there were 2484 rows of data. And after removing the outliers, there are 2451 rows of data. So a further 33 rows of data have been removed. And the figure on the right shows the box plot of each feature after removing the outliers. And we can observe that the dataset is more represented better, the removal of the outliers. So moving on to the next slide. In this slide, I'll explain some of the feature engineering or selection performed, as well as further pre-processing. First of all, we delete the MFR feature and just utilize the natural log of MFR for further experimentation. We also use min-max scaling from the pre-processing library of sklearn to convert all features between 0 and 1. The decision to use min-max scaler is because, unlike the standard scaler, it preserves the shape of the original distribution of our data set. And since we already removed the outliers, using the min-max scalar makes more sense. Moving on to the next slide. Here we utilize the 4 regression models, which are linear, ridge, lasso, and the polynomial regression. So we used 5-fold cross-validation, which splits the dataset with a train size of 1961 and a test size of 490 each time. For our evaluation, we used 3 different metrics, which is the R-square, the mean squared error, and the root mean squared error. So moving on to the next slide. This slide shows the results for the linear regression model. So in the slide, the R-square, MSE, and RMSE for each of the folds are given, as well as their average score over the 5-fold cross-validation. And the figure shows a parity plot of the last fold for linear regression. So the parity plot basically shows the straight line in the plot basically is the ideal line where any points that fall perfectly on this line presents the model's predictions match perfectly with the actual measurements. Any points above the ideal line indicate an overestimation by the model, and any points below the line represents an underestimation by the model. And the blue dotted lines, they are the predicted MFR for each of the actual MFR points. And from the spread of the data points, we understand how far apart our predictions are for linear regression model compared to the ideal line. So moving on to the next slide. This slide shows the results for ridge regression, where an alpha or regularization strength of 1 has been set. So the average R-square for ridge regression is also 0.490, and the MSE and RMSE is also given. And we can see that it displays a similar graph compared to the one we got from linear regression. So moving on. The lasso regression, in contrast, does not perform as well compared to the other models, as can be visible from the average scores of the 3 metrics, as well as the parity plot. We see that it gives quite unusual parity plot where the data points are mostly on a horizontal line. Moving on to the next slide. So finally, we utilize a polynomial regression with a degree of 2, and this gives us the highest R-square value of 0.609 and a low MSE and RMSE values of 0.0191 and 0.138 respectively, considering their average over the 5 folds. And in the parity plot, we also observe a more tightly clustered graph compared to the other models. Moving on to the next slide. Finally, this table shows a comparison of all the 4 models using their average R-square, MSE, and RMSE. And we can clearly observe that the polynomial regression model is performing the best with the highest R-square and the lowest MSE and RMSE values, while on the other hand, the lasso regression performs the worst, corresponding to the lowest R-square and the highest MSE and RMSE values. So moving on to the next slide. So this is an end to the third methodology and as well as the first 2 methodologies. And in this slide, we basically make a comparison of each of the methodologies used. So some of the things to be noted here is that the regression techniques, in case of the first, we only employ a linear regression. In the second methodology, we employ a linear as well as some extra nonlinear methods. And in the third methodology, we employed linear regression along with ridge and lasso, as well as polynomial regression. So in terms of removing outliers, the first methodology only removes some specific outliers. The second and third methodology removed outliers. They used the same technique, more or less, using a box plot to help remove any outliers. And as for normalcy, the first methodology adjusted for the normalcy using natural logs, whereas the second methodology used the natural log for MFR as well as a standard scalar. And the third methodology used min-max scaling to preserve the distribution as well as a natural log of MFR. So moving on to the next slide. Here we present some of the comparative results that we got from each of the methodologies. So each methodology has shown to have its own sets of benefits and disadvantages as well. So the first methodology that has been employed is fairly simple, and it can be written as a linear regression. And by not removing the outliers, it may perform better in some of the more extreme scenarios compared to the linear models which did remove outliers. Also, it may have an impact on the performance when it comes to a regular data set. And we find that this methodology has the best linear model in terms of R-square. The second methodology, having addressed the outliers, negates the worry of not removing outliers. And also, it demonstrates additional nonlinear models, which turn out to perform the best overall compared to all the other methodologies. And finally, the third methodology adjusted both the normalcy and managed the outliers and produce nearly equivalent linear models compared to the first methodology. However, the employing of the technique of polynomial regression turned out to perform the best in this case. So my groupmate, Michael, will go on to explain the conclusion.
Having used various techniques, and we see that the relatively comparable results can be reached in a variety of ways. Various data cleaning techniques can also be produced rather significant different results, and so must be compared to best match the goal of the model. It's also noted that it is important to recognize the units of the predictive variable, as that impacts the method of comparing different models, such as MSE and RMSE. Future work can expand on what's been done, both by adding new data as well as addressing more of the nonlinear models, such as support vector, k-neighbors, and new support vector models, which outperformed in this analysis other linear and polynomial models. It's important to again be sure which of these techniques best match the goals of the model.